Building a distributed database system meant to scale indefinitely requires a complete rethinking of physical infrastructure and software architecture. We are going to architect a distributed key value store capable of holding 5 petabytes of data distributed across 10,000 individual replication groups while maintaining absolute data integrity. This triangle illustrates the CAP theorem, which forces a strict engineering trade-off. In our system, we are choosing strict consistency and partition tolerance, willingly sacrificing availability when necessary. We operate under the absolute rule of strong consistency. A read immediately following a successful write must always return that write's exact result, without exception. We reject eventual consistency models entirely. Rather than returning stale or incorrect data to a client, this architecture will intentionally drop the request and take a localized outage. Enforcing this level of strict consistency at a petabyte scale means monolithic, single-server databases are entirely out of the question. To understand how a massive, globally distributed cluster functions, we have to deconstruct it down to first principles, starting with the mechanical limitations of a single physical server. This schematic details a baseline single-node setup. Incoming data hits an append-only log on the hard drive before being pushed into a branching LSM tree for indexing. Data enters the log first because sequential writes to a physical drive are computationally cheap and highly performant. We replace the single node with a replication group of 3 identical servers, 1 leader and 2 followers. Client requests route exclusively through the leader, which duplicates them to the followers. The leader returns a success signal only after a majority confirm the physical write. By forcing all traffic through a single leader bottleneck and requiring quorum confirmation, we guarantee data durability across multiple drives without violating our rule of strong consistency. Watch what happens when 2 clients attempt to write different values to the exact same key at the exact same millisecond. Without traditional database locks, these competing writes create race conditions, risking split brains or unpredictable overwrites. Our lock-free solution is a globally unique 16-byte sequencer attached to every record. The first 8 bytes record a highly precise nanosecond timestamp. The next 4 bytes generate an incremental sequence number for simultaneous requests. The final 4 bytes capture the unique node hardware ID. The system enforces a deterministic last write wins rule. When concurrent writes collide, the database compares these monotonically increasing sequencer values and accepts the higher number. The sequencer functions as an absolute mathematical clock. It allows the cluster to handle massive I/O storms and resolve conflicts instantly, bypassing severe table locks. A single replication group is physically constrained by the storage capacity of its local hard drives, maxing out around 5 terabytes. To reach petabyte scale, we must partition our dataset across thousands of independent replication groups. How does a client request find the correct group? We introduce a metadata manager, the centralized brain of the cluster. It holds a map linking alphabetical key ranges to assigned replication group IDs. But if every client queried this manager to find their data, it would create a catastrophic bottleneck, collapsing the system. To protect the brain, we deploy stateless request managers behind the load balancer. They cache the routing map into local memory. Now, client requests hit the load balancer, pass to a request manager, check the local cache, and route directly to the group leader. By completely decoupling the state map from physical storage hardware, we achieve true horizontal scaling, adding hardware infinitely without rewriting core logic. Uneven data distribution is the primary operational threat. If specific keys experience extreme input, the assigned replication group chokes, creating a hot table. We automate the response to this using a control plane, an orchestrator monitoring group telemetry to execute dynamic shard migrations. The control plane calculates a logical split point, separating keys A through C. It updates the metadata manager so request managers route new writes for A through C to a new group. The original group then heavily copies all historical data to the new hardware. This creates a critical vulnerability. Historical data is in transit, but new writes are landing elsewhere. We must safely serve read requests during this window. During migration, request managers duplicate incoming read queries and fire them to both groups simultaneously. Receiving both responses, the manager compares their 16-byte sequencer IDs and forwards the most recent data. Once the historical copy finishes, the control plane executes a clean, zero downtime cutover. Relying on sequencer math rather than database locks allows the control plane to execute shard migrations safely while under live production load. This wide schematic shows the fully realized architectural topology we have built from first principles. We abstract routing away from physical storage by pairing stateless request managers with a centralized metadata map. We enforce strict durability and consistency through single elected leaders and quorum rights at the group level. We resolve complex distributed race conditions using the strict mathematical logic of 16-byte sequencers. In systems engineering, infinite scale is a theoretical abstraction. Every physical architecture has a hard ceiling where hardware limitations override clever software. The ultimate bottleneck of this exact design is the physical RAM capacity of the request managers. Because they must hold the entire cluster's routing map in local memory to maintain speed, scale stops when the map exceeds available RAM. Physical limits will always dictate the final boundaries of an architecture, but by combining decoupled routing, strict quorum consensus, and dynamic control planes, we can engineer databases that push those boundaries straight to the petabyte threshold.